All right, let me pass around the sign-in sheet for today. And if you added your name yesterday, this is the same sheet from yesterday, so I haven't updated it yet. But go ahead and sign in. Thank you. So any questions up to here? Lots of chat going on Discord last night, and lots of issues logging in, and I think we've gotten those squared away for everybody. If you wrote me yesterday about not being able to get into the server, I've written back to you either having created an account or reset your account or reminding you of the instructions for logging in. So I believe everybody's able to get in at this point, but if not, definitely let me know as soon as possible through email. If you really need to catch my attention in particular, right, do it through email, because Discord is large and I'm not always going to see everything that's in there. But if it's a general reach out for, I don't understand what GitLab is, what are we supposed to do, right, Discord works. But for login issues or things like that, definitely shoot me a direct email and we'll get you squared away. So I talked to a teacher once who told me that when he has something really important to say, he would stamp his foot 3 times to get everybody to look up, and then he'd say something really important. That's too much work for me. So occasionally, while I'm lecturing, you'll see this pop up on the screen. That means I'm about to say something really important. Okay, doesn't mean that everything I say is not vitally important, because of course it is, right? No, not really. Because 5 hours a week for 11 weeks, that's a lot of talking, okay? And the really important stuff will generally get, reiterated over and over and over again. But, if I'm about to say something like, okay, this will definitely be a question on the exam, that's something you want to pay attention to, okay? Or, I'm going to tell you how to save yourself 5 hours of lost time on this assignment, because I'm going to tell you the most common mistake that you're likely to make, right? I'll throw something up there that says, hey, pay particular attention right now. So you'll see that pop up occasionally. That's what that means. A couple of other things I wanted to mention. There's an engineering computer science club that meets every Friday in room 126. We meet at 12 o'clock. And it's a fairly informal thing to just go in and drop into this club. It's run by students, it's organized by students, it's for students, and it's basically just a chance to hang out with fellow engineering computer science types and kick around ideas. Sometimes there'll be presentations, sometimes the club will organize a field trip to Reed's nuclear reactor or Bonneville Dam or Intel or wherever the club decides they want to go. And it's totally a student thing. So sometimes they have food. I think last year they had pizza at most of the meetings. But that's because the people who were in the club took a vote and decided, yeah, let's go ahead and spend some of our money on having pizza every meeting. So it's worth checking out. Fridays, 12 o'clock, room 126, the room right down at the end of the hall, around to the left. And that goes on all quarter starting this Friday is their first meeting. All right, I've also gotten several emails from people who have gotten onto GitLab and have added me as a reporter and have actually gone ahead and finished homework 1. So we're going to talk about Git a little later today, and we'll get up to speed on that. A lot of people have done the first one-day program, ODP 401, and that's going well for most people. Any questions about doing that first ODP? It's due tomorrow morning at 8, and you have to assess it online using the assess command. So any questions about that? Hopefully everybody's at least taken a shot at doing this at this point. All right. Let me talk a little bit about Unix and leading up towards working on shell scripting. So the first part of this course, the first week or two, we're going to work basically with programming in a Unix environment. Not programming in C, but programming what's called bash. Bash is the thing that we use to type in our Unix commands to say compile and so on and so forth. And there's a whole scripting language inside bash. If you remember the old days of DOS, you could write batch files. They had a .bat extension, and you could say if this, and you could have variables and things like that. Same idea for shell programming. But shell programming is extremely powerful. You can do a lot of useful processing in it, and it's very flexible, and it's a really nice tool, especially for getting on the air really quickly with something. You don't have to compile and link and all this kind of stuff. So let's talk a little bit about Unix. Unix was developed in the 70s at Bell Labs, okay, like Ma Bell phone company, Bell Labs, their research wing. And it was developed primarily for internal use initially. And it was built around some really powerful ideas. It was designed to be modular. Part of the philosophy, and this is all hearsay to me, I wasn't there, but part of the philosophy was the idea of, instead of making a huge operating system with 5,000 commands that do all these particular things, make a very, very simple operating system that is in some sense extendable. Okay, you can have more commands added to it, and try to set it up in a way that these commands can work together with one another. And I'll give you a specific example of that in a minute. But so this modular design, small pieces with well-defined functions, is one key of Unix. A unified file system, and in Unix you'll hear me say everything is a file. Your Ethernet adapter, your keyboard, your display, your CD drive, everything is a file. And files are always treated the same way. They have certain ways of controlling access to them, permission bits. There's ways that you open them, read, write, close, delete, rename, and so on. And that works whether this is a file called homework 1 that you're writing for your 224 classes. This is a file called TTY USB 0, which is a USB port on my laptop, right? They're all treated the same way to a large degree, and so that simplifies your code. If you write code that works on one thing, it'll probably work on something else, even if that something else happens to be a piece of hardware. And inside the operating system, there's this notion of a shell. A shell is the thing that you use to communicate with the system in some sense. So I have a Linux machine as my laptop, so I can just bring up a shell anytime I want. But if you're on the server, linuxengrcs.com, after you log in through PuTTY or SSH or whatever your client is, you get to something that looks like this. And basically, you know, I can say things like, what is today's date? And use the date command, and it'll tell me it's Tuesday, September 24th. Date is not a built-in command for Unix. It's not part of the Unix operating system per se. Date is the name of a program. And somebody wrote a program that when you run the program, it will look inside the system and find the information that contains the date and then print it out in this nice format. But it's just a C program. And I can say where is date, and it will show me that there's a file named date in this directory called bin. That's the program that's being run when I say date. But it's just a C program. And you can go online, you can find the source code for it, and you know, you could take that source code, you could modify it, and make your own version of date. And you could set it up so that when you say date, instead of running /bin/date, it runs /home/your username /mydate, and it does something different. And almost every command that we use in Unix or Linux is really just a program. When you say GCC to compile something, GCC is not part of the operating system. It's a program. It's a program sitting under /usr/bin. What was this program written in? It was written in C, which is kind of like self-referential, which is kind of cool. It's a C program that if you give it the name of something that contains C code, it will go through it and it will turn it into an executable file for you. All right? But it's a program. It's a program that anybody could have written if they knew how. I can say who's logged into the system. Well, I'm the only person logged in because this is my laptop. But who is another program written in C? Okay, I want to connect to the Linux server. I'm going to say SSH $Linux. SSH is another C program, right, which does all the things necessary to make a connection through the network to, in this case, this thing that I've called $Linux. $Linux I've set up for myself to be a shortcut for nick@linux.engrcs.com. So normally I would say SSH nick@linux.engrcs.com. That's a lot of typing. So I've set up my environment here, so if I say $Linux, it's a shortcut or a variable that's equal to nick@linux.engrcs.com. So if I just say SSH $Linux, it's like I'm trying to type in that whole big long thing. And I've also set it up so that my laptop and the Linux server have a secret handshake. And if they both know the secret handshake, I don't have to type in my password, right? And this is part of my mantra as a geek and a programmer. My mantra is don't waste my time, don't get in my way. Okay, that's what I kind of insist on from computers. Having to type my password every single time that I want to log in, and if I type it wrong, I have to wait a few seconds and try it again, and I have to remember my password. That's wasting my time, right? So set up a secret handshake. I can get in there really quickly. All right, so here I can say who, and there's a number of people who are logged into the system. Patrick and Nicole and so on and so forth. And you can see their usernames, you can see when they logged in, you can see the internet address that they're logged in from, and all kinds of information. But they're all just commands. So Unix has this modular design, unified file system, and this idea of a shell. So bash, which is this program that's running right now that waits for me to type something, and then comes back and says, I don't know what you just typed, right? That's another C program. It's a program called bash. So in the early 90s, somebody started to work on a pet project, which was to come up with their own version of Unix that they would write themselves. And so they were writing a few pieces of the Unix operating system, and this is what we call Linux today. And it was just a little pet project this person was working on, and it just caught on and went crazy. And Linux is everywhere now. Unix was a commercial product. It was fairly expensive to get a copy of Unix. What was really expensive was to get the source code for it. The source code at the time I was doing this, which was in the early 80s, the source code from Bell Labs cost something like $40,000 just to look at it. Right? So if you wanted to make your own version of Date or GCC or Who or something like that, you could write it yourself from scratch, or you could get the source code and modify it. But the source code was proprietary, and you had to sign all kinds of things if you were going to get access to it and so on. Linux is totally open source. Okay, there's versions of Linux you can buy, and they come with support or bells and whistles and so on, but there's also completely free versions. Ubuntu, which is what I'm running underneath here, is totally free, and the source code is freely available. And it's freely available as in no cost, and also as in you can do what you want with this. You can modify it and change it around and redistribute it and so on and so forth. So open source is a thing, and there's details to that we don't have to go into yet. So Linux popped up in the early 90s, and it's sort of ubiquitous at this point. And if I say Unix, I probably mean Linux from this point forward. Because most of us don't run Unix anymore, which is the commercial version. All right, so there's things we can do in Unix. It's an operating system like Windows. Windows is kind of point and click, right? So you want to do something, you find the icon and you click on it. If you can't find the icon, you find a folder or a menu and you start clicking until you get to the thing that you want to run, and then you click on it. And you can do that with Linux. There's front ends to Linux. Ubuntu and Mint and all of these come with graphical front ends. And you know, I've got a graphical front end on here. I can you know, click on things and make things happen. And I think I've actually suppressed my menu button, but I can bring up you know, menus, and if I want to do something educational, I can go here and click on this and so on. So it's still got the GUI front end that we're used to from Windows, but that's all kind of sitting on top of what we call the command line. Okay, and the command line is basically when you're sitting at something like Bash and you've got a prompt here saying, here's a blinking cursor, it means I'm waiting for you to do something. And so, you know, you can do whatever. And if you don't do a command name that it understands, it's going to say command not found. But I can say GCC, which will compile. And I got an error because I didn't say what to compile. But, you know, I'm running the GCC command. Or GCC -- help, and it gives me this big long list of quick help on the GCC compiler. So that's our basic environment. We're sitting in this program. This program is running right now. It's called Bash. And I can say PS. PS is another command. It shows me the status of different processes that are running on the system. So most computers run more than one thing at a time, right? They're doing things in the background. I'm sitting here and I'm typing, and it's echoing what I type, but my clock is also updating automatically. And if email comes in, my mail program will take it and it will throw it into my inbox, and it will put something up saying you've got mail. So all of these things are happening simultaneously. So if I say PS right now, I get 2 lines of output. The first line says Bash, and that's telling me there's a program named Bash which is currently running. That's this program that we're looking at right here. There's a second line here which says, yeah, there's another thing which is currently running. What's it called? It's called PS. Well, that's the command that I just typed right here. So Bash is sort of the shell. It's the background thing that's waiting for me to type stuff in. But since I said PS, it started running this program called PS, which produced this output. And part of that output includes this line that says, hey, PS is running. I can say PS-F is full, U is username, and I can put in my username. And my username is Nick, because I'm the teacher, so it's not first initial, last name, because that's too much typing for me. So this is showing me the full list of processes associated with user Nick, and there's a bunch of processes running on my account right now. Here's the Bash thing which was running that we just saw. Here's the PS command that I just typed in, PS-fu Nick. And there's all this other stuff sitting out here running, these things that say assess. Well, these are the assess jobs that I've queued up for your one-day programs coming up through this week. And they're just kind of sitting there. This one is sleeping for 1,000,000 seconds and a little more. I think that's the one that opens Tuesday morning. Alright, so there's lots of processes running on the system. And if I do PS-ELF, ELF, that shows me every process running on the system, and there's a whole bunch of those. And some of these are system processes. The user ID is root. Root is the system owner, basically. And some of these are being used by students, and some of them are being used by other processes like www data, which is web support, and so on and so forth. Alright, so there's tons of Unix commands, and let me give you a standard disclaimer here, right? If this is Unix, this is how much we're going to learn about Unix. Okay? There are this many commands, and we're going to learn about this many. Okay? I probably use 20 or 30 Unix commands, and that's about it. I haven't actually counted this, but it's the top of my head guess. Really, really small subset of the commands out there. But you can put commands together in lots of different combinations and get lots of power out. For example, I'd like to know how many processes are running on the system right now. Well, there's a switch that I can put in here. If I say -elf, I could put another switch on there and it would tell me how many processes are running. I don't know what that switch is. Just this one command, there's probably, you know, hundreds of different things that you can do with it. You can probably find a book from O'Reilly that lists all the different ways to use this one command. I don't know that. I know like 3 versions of it, and you've seen them all now. There's a command called WC, word count. And WC does the following. Whatever you type into WC, it tells you how many lines you typed, 4 lines, how many words, things separated by spaces, and how many characters total. So if I were to take all of this information that came out when I said PS-ELF, and I were to type that into the WC command, it would tell me how many lines of output there were. That would tell me how many processes there were. So I've highlighted all of this with my mouse, and I've got this set up so if I just hit the middle button, it basically pastes everything that's been highlighted. And it tells me there's 167 lines. So I know there's about 167 processes. There was 1 line of header in the beginning, so it's really only 166 processes. Well, copying and pasting is kind of a pain, right, the way I just did that. Turns out we don't have to do it. Okay, so there are mechanisms, and we'll spend a lot more time playing with this later, but I just want to kind of introduce this idea right now. There's a way to take commands and put them together. What I really did here was I did the ps-elf command, and I wanted to take all that output and feed that into the word count command. And I did it by taking this, copying it, and then running word count and pasting that as input. But there's an easier way to do that. We can use what's called a pipe. It's a vertical bar. And I can list another command here. And what this basically says is execute the command ps-elf. But instead of showing me the output, send the output to the input of this WC command. And that's going to do exactly the same thing that we just did. It tells me there's 164 lines from the PS output. So I don't know how to tell PS to count the number of lines that it produces in output, but I know how to use WC. It's one of those 20 or 30 commands I know. And I can put those together. Let me give you one more example of this, just to kind of like motivate that this is actually useful. So the assess system. So this morning I was curious how many people had tried to assess their code for ODP 401. So inside this directory I've got the output of the assess command generates this grade file. I've X'd out the grades here. But any time that you try to assess your code, it creates a new entry in here that basically tells you what your grade was, when you did the assessment, and so on and so forth. So I wanted to know from this file how many people had tried to do the assessment. Well, I could just word count this file and it tells me there's 66 lines. That doesn't mean there's 66 people, right? Because some people tried more than once. So there's a command called awk. We'll spend a few days towards the end of the term talking about awk. And awk is a command that basically lets you break files up into columns. And by default, it separates columns by spaces, but I can say awk, and I can do what's called putting a switch on this. So switches are ways that we modify the behavior of commands. When I say ps-elf, elf is a switch. It's actually 3 switches that modify the behavior. So awk, I can use a switch f, which says I want to specify a separator other than a space. So I can say -f colon, and now I'm saying I'm going to give you some input that's separated by colons. And awk takes a second argument, which I'm going to say print $2, which means print the second column of this file. So it's going to take whatever I feed in, it's going to take the second column separated by colons, that's going to be the username. And then I'm going to give it the name of the file, tgrades.txt. And now I've got a list of usernames who have tried to use assess. Well, if I put that into word count, I still get 66 because there's still duplicates in there. I'd like to get rid of the duplicates. Well, there's an easy way to do that. If I pipe this into sort, which says sort things alphabetically, all the duplicates are sitting next to each other. And if I pipe that into another program called unique, that says if this line is the same as the previous line, get rid of it. Take your input and only show me one version of that line. If there's multiple versions after it, ignore them. And so this will show me unique usernames. And then if I pipe that into word count, now I see 33 people have tried to use assess. Okay, that took about 25 minutes to go through just now, but if you understand these pieces, awk, sort, unique, and word count, and you will understand these 10 weeks from now, right? It takes you about a second to type this in, to think of this and type it in, and now I know how many people tried to use the assess server. And if I'm going to do that repeatedly, I could make my own version of a command. I could say something like alias go equals, gotta spell alias, equals all that stuff. And now if I just say go, it does my count. Oh, I messed something up though. That's awkward, no pun intended. Huh, okay, I did something weird. Ignore that. Anyway, you can set up an alias to do that same thing, or you can make a shell script, which is where we're really going to go with all of this stuff. There we go. Don't worry about the details. We're going to go over all that. But basically, I made a file called Go, which contains this set of bash commands, Unix commands, right? And if I say Go, it's going to execute Go from this directory, homenick assess cse go, and it's going to execute those lines. Okay, so this is the kind of thing that we're moving towards being able to do. And for me, the key is not trying to learn every Unix command that's out there. The key is trying to learn a sufficient kernel of commands and get fluent in how you put them together so that you can conjure up a solution to whatever it is that you're trying to do. Okay, it's your toolbox basically. You don't have every single tool from Home Depot sitting in your little toolbox. You have 2 or 3 good types of screwdrivers, you have a really good hammer and a pair of pliers and a few cutting tools and so on, and you know how to use them. You know how to put them together. Okay, so a lot of this course is about toolbox building. Same thing when it comes to debugging and so on and so forth. And your toolbox will look different from someone else's toolbox. It'll look different from my toolbox. It's whatever is going to fit your personal style. All right, questions on that? All right, so let me talk about Git at this point, and then we'll go ahead, because the Git homework is due on Friday, and then we'll start talking about more Unix commands, and we'll start working into shell scripting, because your first programming assignment is a week from Friday, and that's a shell scripting assignment. And the ODP starting tomorrow will start building up on what you need to know to do PA1. But we got time to get there. So so how many people went ahead and joined GitLab yesterday? Cool. All right. What's the best way to do this? So if you go down to page 5 on this how-to, there's 2 or 3 pages of notes on GitLab. So there's a few aspects to Git. Git is, first of all, a source code control system that you can use totally on your own from anywhere, right? So let me hop over here where I've never done anything with Git, and let's do some Git setup. So when you start using Git, you have to do this one-time command to basically tell it you want to use VI, unless you want to use some other editor. I think it defaults to Nano or Pine or something, but I'm going to go ahead and use VI. So I'm going to do git config global core.editor. VI, and that'll set me up. And you only have to do that once in the life of the account, right? You log out, you log back in. It remembers that. If you're on a different machine, you have to do this differently. So when you're working with projects, you usually want your projects to be in their own directories, okay? And we're still going to spend some time going over basic Unix commands, but you don't need to do that for homework 1, but you've probably seen this in 121 anyway. So you know there's directories, right? Folders, whatever you want to call them. And you can see what your current working directory is with pwd. It's /home/ whatever your username is. Okay? You're going to be using this server for 224, 222, and 223, possibly 223. So first thing I would do here is make a new directory called 224. And I can change into that. My current directory has stuff from yesterday. I'm going to change into directory 224. And if I say list the files in there, there's no files in there. And if I say print my working directory, it's Goblin King /224. Okay, I'm going to make directories underneath here for everything that I'm going to do. I'm not going to do all my work in this one folder. So I want to play around with Git. I'm going to make a directory called Git Test. And I'm going to cd into that. And that's also an empty directory. And if I look at my working directory, it's home Goblin King 224 Git Test. And I can do whatever I want here. I can edit files and so on and so forth. Right, so I've got a README sitting in here, but when I first log in and I'm sitting under this original home directory, that README file doesn't show up, right? It's in a different folder. So I'm going to go back down to Git Test. There's my README. Okay, so you want to start using Git. So one time per project, you have to say Git Init. That tells the Git system you're trying to use source code control in this directory. So Git Init, and it just says initialize an empty repository, and it tells you what directory you're in. Okay, if I look at my files in here, I still just see my README, but there's actually a new file in here. There's what's called a hidden file, and it's called .git. And if you say ls, put a switch on that command, which says show me all my files, you see there's a directory called .git, and I can cd into .git, and there's a bunch of stuff in here. Okay, don't ever mess with this stuff. It's hidden for a reason, because if you start tinkering around with the stuff in here, you can corrupt your repository. And Git is supposed to be saving, every version, every time you make a change and commit it, it should keep all that history for you. You can lose all of that if you monkey around with this, because it's all just a bunch of files organized in a very particular way that's meaningful to Git. So it's a hidden file, keep it hidden. Okay, don't play around with it unless you want to explore it and see what's going on, and it's not your final project that's due in 2 hours. You can go around, mess around with it and explore. But for stuff that's important, leave it hidden. All right, so we've got a file in here called README. We want to put this under source code control. So git add and the name of the file you want to add. Okay, and every file that you want to put into your Git repository, you have to say git space add space and the name of the file. And you can do those one at a time if you have multiple files. You can use wildcards. So if you want to add all your .c files, you could say git add star.c. If you want to add everything in your directory, you can just say git add star asterisk. And it'll take everything that's in there and it'll put it under Git source code control. And that's usually what people do, but it's really not what you necessarily want, because you don't need to source code control the executables. You really want the source files themselves to be what you track. Right, that's the source and source code control. But let's just add the README. All right, doesn't say anything, that's good. Unix tends to be silent. Okay, it doesn't jump up and down and celebrate every time that it successfully does something. If you ask it to add a file and it succeeds, it just comes back with a $sign. It's not going to say Unix has successfully added README to your repository. It's silent. Silent is usually good. Now, if something goes wrong, right, it'll tell you, hey, fatal error, you tried to add haha, but there's no file in here with that name. Okay, so no response, usually a good thing. All right, and then after you've added your files, you say git commit. And git commit basically pushes your files that you've added into the repository. So it's a staging area. You've got your files, you move them to the stage with the add command, and then you push those into the repo with commit. So git commit, and oh, I forgot to do something. I forgot to tell it who I am. All right, that's shamelessly missing from this README. It's down here under this initial GitLab setup. So you need to do these two things also before Git will work. If you're doing it all at the same time, the order doesn't matter. All right, so let's do this. Let's do git config global user.name. And I'll just add my name. And let's do user.email. Whatever your email is. Okay, so now I can say git commit, and it brings up an editor window. This is why you specified what type of editor you wanted to use in the beginning. It brings up an editor window, and you can type in here a message that says, why are you pushing this into your repository? What changes did you make? Okay, so it's kind of forcing you to do a little bit of housekeeping. And if I just, kick out of here, it'll say, hey, you didn't actually type in anything. I'm not going to commit this. So you got to type at least something. So I'm just going to say right, initial checking check-in of a README file to demonstrate Git commands. And it tells me one file change, one insertion, create mode, other stuff like that. Okay, so here it does give you some feedback, but it didn't say fatal or error or anything like that. So we're good. Nothing has apparently changed. I've still got this README sitting in here. It's still got, this one line in here that I typed in. Nothing has visibly changed to me, but it has added this file to an underlying repository. So you can say git status, and it will say there's nothing to commit, your working directory is clean. That means everything's up to date, everything has been committed. Now suppose I make a change to this README. And I say git status, my directory is not clean anymore. There's changes that have not been staged, in particular this file README has been modified. It's telling me I've made changes to this file, but I haven't pushed it into the repository yet. And if I try to commit, there's nothing to commit yet because I haven't pushed it onto the stage, right, into the staging area. So you make a change, you want to push it in, you got to do add and you got to do commit. All right, so git add readme. And if I look at the status here, it tells me I've got this ready to commit, right? I just need to say git commit. So git commit, and I'm just going to put in a period for my change message. And now I'm back to a clean directory. But I've added this change to my repository. And there's a history under that .git file that basically records everything that has happened to this file. So I can say git log, and it will show me a fairly complex looking view of what's happened. At 10:41, this line down here on the bottom, I made a change and I saved it with the comment initial check-in of a README file. At 10:43 in 5 seconds, I made a change. I didn't put in a good message, I just put in a dot because I was in a rush. But it doesn't really tell me what I did. But I made some kind of change to my README file and push that into the repository. So put in good messages on here so that if you need to go back and look at an old version of your code, you can figure out which version you want. And using this magic number, I can go back and retrieve the version of this file when I did this commit. So if you accidentally delete half your code, you can go back and get the version before you did that. All right, same thing with Unix. This is Git, this is what we're going over, okay? Really, really, really narrow path through the whole space of how to use Git, but enough to do everything that we need to do. Okay, so that's Git just on one machine. This is all sitting, in this case, in my directory on this server. If I delete this directory, everything is gone. If the server goes away, if I forget to pay the bill and they shut down the server and delete everything, all this is gone. I won't forget, it's automatic. It's all local to this, okay? What you'd really like to do and what you need to do for turning in assignments is take your repository and make a copy of it off on a server somewhere else, okay, in the cloud. And there's a lot of Git servers out there. The main one used to be GitHub. That was sort of the first really major one that was out there. And as I mentioned yesterday, to be able to have repositories that were private that nobody else could look at, you had to pay. And then GitHub got bought by Microsoft, and lots of people kind of jumped ship at that point. Some people came on because of that. But GitLab has been around for a long time, and they let you have private repositories for free. So this is free storage, right? A repository can be up to 10 gigabytes. And what's the limit on the number of repositories that they allow you to have? There's no limit. Okay, so theoretically this is infinite storage. Now it's not the kind of storage that you can just throw your photos on and pull up on your phone and easily look at your photos, because you've got this whole Git system on there, right? It's really not tailored for that kind of thing. But for source code, for projects, for putting things up there, for keeping track of versions, it's effectively unlimited. Right? 10 gigabytes is a lot, especially if you're good about only pushing up source code, right? The actual files that you're writing and not the compiled versions, which could easily, be hundreds of megabytes each. But 10 gig of source code is a lot. Okay, that's 10 billion characters that you or someone has to type in VI. That's a lot, right? Even with different versions. So it's essentially free, unlimited storage. It's presumably very reliable. They do their backups and that kind of stuff. It's presumably very secure, and you can access it from anywhere with an internet. So I have a version of GitLab called Lab Code running on my phone. I'm at a restaurant in Frederick, Maryland, eating pizza with someone, and I want to show them something from a project. I pull out my phone, I run Lab Code, and I can download the code that I pushed into there from my system at home, right? And it's not me who's managing all of this. Somebody else named GitLab is running all this stuff. I'm just using it. So it's a really, really nice habit to get into. It's a habit that you'll probably need to use at a university and that you'll probably need to use in the workplace. And it might be GitLab, GitHub, it might be their own server, but the same idea. And there's other source code control systems besides Git. There's Subversion and RCS or CVS if you're old school and things like that, but similar ideas. Right? So Git is a good one to learn. It will definitely serve you well in the short term, and the ideas of it, the habits of it will help you down the road. You got a resume, you can put a one sentence that lists what your GitLab or GitHub repository is, and now they can go and they can look at your work and see code samples and things like that. And employers know how to do that. So it's a really good thing to get comfortable with. All right, we got 2 minutes left. So let me just tell you what you can read if you have not already done this. Go ahead and get yourself a GitLab account, gitlab.com, sign up, give them a real email address, pick a username, hit the confirmation link in the email that they send you, and you should have an account after that. And then if you've done all of this and you've done the username and email setup, make sure this is the email that that you gave them. Make sure this is the username that you set up with them. Okay, so I would get your GitLab before you do these steps. And then there's some other stuff you have to do, some one-time stuff. This is setting up that secret handshake so that you don't have to put in your password every time that you want to push something over. You never saw me type a password when I was saying Git Commit and things like that. And when I push these things to the server, I just say Git Push or Git Pull. And I don't type in a password. It's all set up through this public-private key handshake. So we'll run through that tomorrow. I'll just show you the process, but you can usually figure it out because when you set up your first, when you start an account at GitLab, it'll say you need to set up an RSA handshake, and it'll give you these instructions basically. We'll play around with that, and we'll run through this tomorrow. And then it's 3 more commands to do all this stuff in the cloud. Git remote add lets you push something over to the cloud. Git push lets you push your changes over, and get clone lets you take a repository from the server and pull it down to your local system. And with those 3 things, you've basically got everything you need to move around Git. So we'll work with those tomorrow, and then we'll start talking about shell programming and how to do scripting, and we'll go into more Unix commands and just keep building on that. All right, so I'll see you tomorrow.